Hello, good evening. Welcome back to our live tutoring classes. In this class, I'm going to take you through the whole concept of AC circuits. So this is an applied electricity live tutorial class. So taking alternating current as the focus of this class. So alternating current. So let's ask ourselves, we have two main sources which we can think about. We have the direct and we have the alternating current. So previously in the circuit terms, you use direct current as your sources. So you realize that a current will pass through a conducting wire and also move through a load, and that current will be produced by a source like this. So a current which is constantly moving through the wire without changing. So at any time t, a direct current has the same value. So it doesn't change with respect to time. So meaning that if you have a direct current, the quantity of electric charges produced at any point at any time is constant. So it's constant. Now, in this class, we are going to deal with alternating currents. So as you hear, alternating, meaning that it goes up, it comes down, it goes up, it comes down. It alternates, that is, it changes and it repeats itself. So let me give you a real life example of alternating current or real life applications of alternating currents. Now, whenever you have an alternating current, this current increases from zero, then it moves up until the peak. So you are going to have, let's say, let me draw my plane. So here 0, negative, sorry, -1, -2, 1, 2, 3. So an alternating current is going to increase from 0, and it will increase until it reaches a certain point which we call the peak value. Peak value. So every alternating current or alternating voltage, so if you have an alternating current or alternating voltage which is changing with respect to time, it will increase from 0 until it reaches a peak value. So once it reaches that peak value, then it starts to decrease, then finally back to 0. So that is the nature of alternating current. So let's say you have a naked wire and you touch the wire. You realize that an alternating current will rise from 0 to the peak, then after it will come back to 0. That is why in our homes, whenever you touch a wire or let's say a socket which is faulty, you realize that once you touch it, you get a shock, but it instantly what leaves you, right? So the reason why it left is that it has decreased to 0, and at that point you are free to take off your hand. And I tell you, if you have a direct current passing through a wire, and if the direct current is of magnitude which is capable of electrocuting you, then you are going to be part of that circuit. I mean, it's not going to release you because alternating current doesn't change, and the value of the alternating direct current passing through you will remain constant until you die. That is why direct current is generally dangerous as compared to alternating current. So direct current is very dangerous as compared to alternating current, because for alternating current, once it shocks you, it releases you at a point in time, setting you free. That is why it can raise somebody and bring the person down. But for direct current, once you get shocked, you remain part of the circuit and you are constantly being electrocuted. So that is the main difference between alternating currents and direct currents. But as I said, this video, our focus is on alternating current, not direct current. So Generally, it's actually AC circuit, so alternating circuit. So the general thing is alternating circuits. So whenever you have a circuit where the quantity, which is whether being a current or a voltage across the conducting wire is alternating, then this circuit is termed as an alternating current circuit or alternating voltage circuit. You get it? So let's see, in alternating current, you have some terms we use. You have what you call the average. Then you have what you call the root mean squared. So roots mean square value. So now let's see. As I said earlier, alternating current starts from zero, then increases to a particular point, then after it decreases to zero. For that reason, if you want to quantify or get the actual magnitude of an AC parameter, you can never get it because at any instant it is changing. So the idea behind it is, because it keeps on changing, we take the average value. So you sum the value from to from zero, and you sum all these values to its ending points. Then after, we find the average within the time interval. So for an AC circuit, the average value is equivalent to the DC value we know. So if you have a source and that source is AC circuit, and you connect it to, let's say, an ammeter, the ammeter will read the average value of the AC circuit. So the value that this ammeter is going to read will give us the idea that upon the changing magnitude of our current or voltage, it sums up to, let's say, 2 amps. That is, when you sum all the different components of our current within that particular time, which is the average, that is what you are getting. So always have in mind that in AC circuit, when you're being asked of average, it's just the DC value of our parameter. Now let's come to root mean squared. So root mean squared is also the effective value. Effective value. So this is a necessary parameter which we'll be using throughout our AC circuit analysis. So we always use the effective value of our AC current or AC voltage. So let's see. For the effective value, we are saying that this is the value. So when you say effective value or the root mean square value, all that you mean is that is the value of the direct current that, when flowing through a given resistance for a given time, will produce the same heat. So we are using heat as a quantity for the effective value. So it is the DC value which, upon flowing through a particular resistance at a given time, will produce the same heat as the alternating current. So without wasting much time, let's see how to find the average and the root mean squared of alternating currents. So let's see. So now let's see average. How do you find the average of an AC circuit? So average of an AC circuit. So to find the average of an AC circuit, all that we do is you simply identify your cycle. So you simply identify your cycle. And after identifying your cycle, the next thing to do is you determine the period. I'm going to explain these terms. So you determine your cycle, then determine the period of the cycle. Then after, you find the area of the cycle. So finally, the average value of an AC circuit is equal to the area of a cycle. So area of a cycle all over the period. So now, what is a cycle? So a cycle is simply a unit of an alternating current. You know that alternating current will move from zero, then it will come back to itself. So depending on the nature of the alternating current, it can be this form, can be this form, like this. So once an alternating current starts from zero and moves and come back to itself, there is something cyclic here. That is, it is cyclic in nature. Take note. So the cycle here is identify the full cycle. That is when an AC circuit starts and when it ends. That gives us the full cycle of an AC circuit. Now for the period is simply the time it started till the time it started again. So you know it is a cycle, so it keeps on repeating itself. So to know the period of an AC circuit, you simply take the time it started and the time it is starting again. So the difference between that time or these 2 points is what gives us the period of an AC circuit. So it's just the time taken for one cycle. So that is period. Then now we just find the area. As you know, area. So depending on the nature of the signal, we can't find the area of that particular cycle. So giving this, we can go ahead to solve some problems here. So let's see. I have this wave here, and this wave, I have voltage here, and I have S, which is time. So on alternating current, you know, as I said, an AC parameter changes with respect to what time. For that reason, this is a voltage which is being changed at a particular time. So it's giving us a shape which is a square wave this way. So it goes and it comes back to its position like that. So we have here to be 0, I have here to be 2, I have here to be 4, then I have here to be 6. So here is my peak value E. Then I also have a peak value which is negative E on the lower side. So I have this here, and this is my pulsating voltage. That is an AC voltage. It is alternating. So this voltage I'm having here, I'm to find the average because it starts from 0, then it increases, and after it comes back like that, like that. So we realize that this AC voltage I have here is not having a static value, so we need the average. So let's find the average of this, which is equivalent to its DC value. So the average is simply equal to, from the steps I said, you identify the cycle. You identify a cycle. After identifying the cycle, you know the period. Then after, you find the area of the cycle. Finally, we do this computation to get our average. Take note. So at this point, where is the cycle? Where is the cycle? So let's see. It starts from here, 0, right? Then it climbs up to this side, which is the peak, maintains at the peak for some this interval, then come back towards its original point. Sorry. So it starts from here, moves, and at this point, you realize that this wave is in two parts. It has a positive and negative. So once it rises up to the positive, it comes down to the negative before it ends. So let's see something here. It started from here, right? So the tip should go this way, like that. So the next part of the wave should also start and move up like that. So you can't stop here. This is because once you stop here, the next part is not moving up anywhere here. This is a resting phase. So you realize that the full wave will move up here, then it will come down. And after coming down, we'll move and start from here. So right now, once it starts from here, it will also go up, come down, and it will start again. So we have notified that this is our cycle. So our cycle is this whole portion like this. So it is this is a full cycle. So we can isolate the cycle and redraw it here, something like this. So this is the cycle. What is the time? And this is our voltage. So this is the peak E. I have the negative voltage down here, which is this. And I have 0, 2, then 4. So once you identify your cycle, I said the next part is to find the period. So it started from here and it's going to start from this side once again, meaning that the period is equal to, period is represented as T, is giving us 4 seconds. The unit here is seconds, so 4 seconds. So right now I've been able to identify my cycle and I've found the period. So meaning that it spans within 4 seconds and come back to its original position. Now, how do I find the area of this cycle? You can see that this is forming a shape. Here is a square, here is also a square, right? Yes, it is in two parts. So now to find the area, you realize that this part and this part is equal, it's symmetrical. One is at the negative, one is at the positive. So finding the area of, let's say here is A, here is B. Realize that the area of A is equal to its side, sorry, this is a rectangle instead. So this length times breadth, right? So length times breadth. And this is equal to, the length here is what? E. Then the breadth is 2. So I'm getting 2E for the A part. Then when I come to the B part, I'm having the length to be negative E times also it is 2. From this side to this side, 4 minus 2 is 2. So times 2, getting negative 2E. But I need a total area. So I need to add these two components together to find the total area. So I'm going to get 2E plus negative 2E. So my total area remains 0. So once I have my total area to be 0, then my average is simply equal to, so my average A of this is equal to 0 over the period, which is 4. Therefore, this is giving me 0. Now, let me give you a general case. Whenever you have a wave which is symmetrical about our horizontal axis, so that the same section which is up here is the same section down here, then you can see that that wave has a 0 average. A typical example is a sinusoidal wave. It starts from here, moves up, comes back like this. So if you identify the cycle to be this way, you realize that this same section repeats itself down in the negative side. So the average here is 0. It doesn't have an average value. It is 0. So we've now found our average A to be what? 0. Now let's go to the second term. I said RMS, root mean square. Root mean square. So I'm showing you how to solve for root mean squared and the average given a cycle. So AC can be represented in an equation form or in a cycle form. So we are now tackling the cycle form. So let's see how we do this. So for the RMS, we are going to have 1. You always identify your cycle. The second part is you identify your period. Then the third part is you identify, or sorry, you square the cycle. So in finding the root mean square, we square the cycle before we find the area of the squared cycle. So area of squared cycle. So these are the steps we follow. You identify a cycle, you find the period, you square the cycle, then you find the area of the square cycle. Then finally, our root mean squared value. Our root mean squared value is simply equal to the square root of the expression, our area of squared cycle over the period, and that is that, and that is that. So the square root of the area of the square cycle over the period. So now in our case, let me bring back our wave. So you realize that we've already identified the cycle in our previous example. Let's use the same wave. I have the peak to be E. So this starts from E, comes down to negative E, then it will move back. So this was the cycle, right? 0, 2, 4. So what the algorithm is saying is first identify the cycle. So we've identified the cycle, right? Now the next step is to square the cycle. Squaring the cycle means that you are going to square everything here. When you square, this becomes what? E squared, right? This place becomes what? E squared. But once you square a cycle, you will never have the negative portion. Everything becomes what? Positive, right? So that is the case. So in the case of square cycle, we will redraw our waveform so that we are having E squared. And for the E squared, we have the first one, which is this part, still at the positive side, and this one will move up because it is now positive, right? It is now positive. So to attain the positive, so now we have our both A and B at the positive end, right? After squaring the cycle. So that's the benefit of squaring the cycle in this manner. So at this point, we still find the area of the square cycle. So I have 0 here, 2 here, and I have 4 here. So with the cycle here, since I have two rectangles, I can find them separately. So finding the area of the first one, I'll have its length here, which is E squared, multiplying its weight, which is from this side to this side, which is 2, giving me 2E squared. Then I'll find the same for B, which is equal to E squared, the same length times 4 minus 2, which is 2, right? This is also giving me 2E squared. So at this point, my total area A is equal to 2E squared plus 2E squared, giving me 4E squared, right? So since I have my total area, the next thing I have to do is to divide my area over my period. And I had my period to be 4 seconds because from here to where it was starting, right? So 4E squared, right, which is my total area all over my period 4, and that is going to this E squared, and this is giving me what? E squared, because the 4 will cancel this 4 and I have E squared. But root mean squared, I said we take the square root of your final expression. So taking the square root of this, I'm going to get my final root mean square value as what? E. And that is that. From this side, let me summarize it, and I'm going to give you the general algorithm. You are lucky that you have a defined waveform in the form of rectangle. But you have some waveforms which you cannot find its area as simple as we did. We can have a rough waveform. So what you do is you take the function. So taking the function of the waveform, you know that a waveform, as I said, that a sinusoidal wave or AC always alternates or changes with respect to time. So it's a function of time. So what you do is whenever you want to find the area or we sum the area, we use integral. So integral from 0 to our period, because we are summing within the time it started to what the time is ending, and that is the period, from 0 to the period, and here is the t, right? So I said you divide this whole expression by your period. So this gives us the average. So mathematically, this is the formula we use to find the average for any waveform. So your function, the t, and you integrate with respect to what? T. From 0 to t, then you divide by your what? 1 over t. That gives you the average. For the RMS, as I told you, after identifying your cycle, which is f of t, you square it. So you are going to get f of t all squared, right? Then your integral 0 to t once again. You have your 1 over t. Then you put everything within the square root. So this is equal to our root mean squared. So generally put this formula down as we'll be using it along our class. So this is all for root mean squared and the average of AC currents and voltage. So now let's see. Let's tackle sinusoidal voltage and current, or we say pulsating. Either you use pulsating, meaning that pulse. So pulsating or sinusoidal. Sinusoidal current or voltage. Right. So this the next subtopic we are going to treat here. So when you talk about pulsating or sinusoidal current, it's basically what you have been doing. So let's see. At this point, generally, if you have a sinusoidal voltage or a voltage which is in a form of a pulse, it is generally represented as V, capital VM, which is its peak value, sine 2 pi ft. Likewise, if you have a sinusoidal current, so normally represents our alternating or pulsating currents and voltages with smaller letters, right? While the peak values are capital. So capital IM sine 2 pi ft, right? So at this point, let's define the parameters within our sinusoidal current and voltage. So this is what you call the peak voltage. So in your alternating voltage, it will rise to a maximum value before it will come down. That maximum value is what we call the peak voltage. So the peak voltage multiplied by this expression here. Now, what's this expression? I have 2 pi f. 2 pi f, you know f is what we call frequency, right? Frequency. But this whole expression is what we call the angular frequency. Angular frequency. So angular frequency. In some literature, you see sine theta, right? So the theta there stands for 2 pi f, right? So the angular frequency by the time, this is time. So this is constant. This is what you'll be putting in the value. So at time t0, at time t1, at time t2, you realize that that will give us different values for our voltage. But this thing here gives us the angular frequency. We have some problems where you'll be asked to find the frequency. So this f alone is the normal frequency we know, but 2 pi f is what we call the angular frequency, represented as omega. So when you see 2 pi sine, so whenever you see sine of omega t, is the same as what I have written here. So instead of 2 pi ft, you can write sine omega t, and they are all the same. So take note of this. You realize that the voltage parameters and the currents are the same, just that this is current. So P current, you have your velocity, angular velocity, and here is your frequency, then your time. So let's see. I have some problems here, but before that, we have what we call a phase angle. Phase angle. Let me talk about this. Now, when you talk about phase angle, whenever you have a linear circuit, as in when we're doing our a DC circuit, the voltage and the current across our conductor are in the same phase. That is, they are not separated at any angle. That is, your current and your voltage lie on the same line when you draw its diagram. the phasor diagram. But in an alternating, because one will start before the other, there is a possibility that your current and your voltage will be at different angles with respect to each other. So we have something called the phase difference or phase angle, which is equal to phi. So when you see the expression Vm sine, then you come open bracket 2 pi ft plus phi, like this. So this is how we represent it. So any waveform with this pi means that the voltage we are talking about is leading a reference voltage or a reference current. So meaning that it is leading by this phase angle. You get to understand all these parameters as we move on. So at this point, let's see these problems here. 1. Find the frequency. Find the frequency of the following quantities. So we are finding the frequency of the following quantities. So I have the first one to be our current I is equal to 10 root 2 multiplying sine 100 pi t. So this is the current, and we've been asked to find the frequency. To find the frequency, you know that your I is equal to your Im sine 2 pi ft. For that reason, we can clearly see that our pi t here and our pi t is here. So they are common, meaning that this 100 here is equal to what? F. Multiplying what? These two. Clearly, right? So let me rearrange this. So you get sine. So I'll make it 2f pi t. And you can see that the pi t is here, but 100 will be equal to 2f. So that is what you do. So you write your 100 is equal to 2 times what? F. Therefore, f, which is the frequency, is equal to 100 out of 2. And that is equal to 50 hertz. So this is how you find your frequency, 50 hertz. So likewise, I have a second quantity, which is V is equal to 100 sine 2 120 pi t. So at this point, I know from the previous example, you can clearly see that our 120 is equal to our 2f, and our f is equal to 60 hertz, right? So that is basically how to find the frequency. You realize that the quantity attached to the sine form is what you call the peak value. So this is a peak value for I, this is a peak value for our voltage. So now let's see. Let's take effective value or root mean squared in focus. So the effective value, or what we call the root mean squared, RMS. When you see RMS in AC, it means that you want to find the root mean squared. So generally, put these equations in mind. The VRMS, which is the root mean square voltage, is always equal to our peak voltage over square root of 2. And your IRMS, that is your peak current, sorry, your root mean square current is always equal to your peak current over square root of 2. So this is a relationship you should have in mind. This is a relationship you should have it in mind. From here, let's take this example. Find the RMS of the following. Find the RMS of the following. So let me bring out the first equation we treated. It was 10 root 2, right? Sine 100 pi t. So we've been asked to find the RMS of this waveform. And I told you that whenever you get such a question, you just write the general form of a waveform. So you know that you get Im. This is I is equal to our current. So you are going to get Im is sine. So your Im sine 2 pi ft. For that reason, your Im is simply equal to 10 root 2. So you've identified your peak current. So in the general waveform, you only have your peak current available. And that is giving us 10 root 2 from what we have here. But the question is asking us to find your RMS. So to find your RMS, we simply divide this by what? Root 2. And this just go away simply. So our RMS current is equal to 10 amperes. So likewise, the voltage, which was V, is equal to 100 sine 120 pi t. So at this point, you realize that 100 is the peak. So Vm is equal to 100. And when I divide over root 2, I should get my VRMS, which is equal to 70.7 voltage. So this is how you find the effective value as well as our frequency given any waveform. Now let's quickly move to the next section, which deals with what we call harmonics. Harmonics. So when you talk about harmonics, let me draw your mind back to what you're doing. I gave you a waveform which was rectangle waveform. You realize that it kept on repeating itself. And this is what we call periodic wave. So we say that this wave is periodic. What it means is this cycle will continue to repeat itself infinitely. So meaning that you only take one cycle in focus, then the rest is the same. But we have some waves which are non-periodic. They are non-periodic. They constantly change and never repeat. So you can have something like this, then it can go up, it can come down. You can have irregular, different, yes. So these waves are not repeating. As it goes, it changes form. We call them non-periodic waveforms. So if you have a pulsating voltage or current in this form, we cannot find the root mean squared as we did in the previous one. So how do we do that? So we simply have a way of finding what we call harmonics. Harmonics is just a series of waves with different frequencies. So here the frequencies are different, but they follow a pattern. They follow a pattern. So we just express a waveform as the sum of what sine waves with different frequencies. But always I said the frequency follow a pattern. So we have F, which is F naught, which is called the fundamental frequency, from which the other frequencies are what born. So fundamental frequency. Fundamental frequency. So when we talk about fundamental frequency, you can have F naught, then the second F1 is what we call the first harmonic. First harmonic. Then we have F2, which is the second harmonic. So you realize that F1 can be equal to 2 F naughts. F2 can be equal to 4 F naughts. And it goes on. So the third harmonic is simply an integer multiplying what? The fundamental frequency. That gives us harmonics. On that note, let's see how to find the root mean squared for a non-periodic wave, or what we call the harmonic waves. So for example, if you have a voltage which is non-periodic, having the form A naught plus A1 sine omega t plus phi 1 plus A2 sine omega t plus phase 2. So this is 2 omega in that order. So you realize that you can sketch this wave whenever you have A naught without the sign, meaning it's a DC value, it's not alternating. So on the graph, this represents something on the ground, something like this. So the wave will first experience from 0, it will remain constant for A naught before it will rise to A1. Sorry, for A naught, let me write A naught here. Sorry, it's not here. This is just the time. So it will rise to A1 at a particular frequency omega t. Then we have A2. It will move again to A2 at another particular frequency, which is what? 2 omega t. So it's going to be different, but there are phase differences for each part. So this is what we call a non-periodic waveform or harmonic. How do we find the root mean squared then? Under normal circumstance, root mean squared is the peak voltage or peak current over square root of 2. But in this case, you draw your square roots, then after you find the RMS for each waveform. So RMS for this, we just square it, A naught squared, right? Plus, what's the RMS for this? I'll take the peak A1 over square root on 2, then I'll also square that, plus the RMS of each of your odds of your harmonic. So each harmonic, you find the RMS. So RMS here to have A2 over root 2 all squared, and that's on. So this is the formula for finding the root mean squared for a harmonic. So let's get a question here. So find the RMS. Find the RMS of the current I of t is equal to 2 plus 5 sine omega t 2 plus, so let me do it all, 2 plus 5 sine omega t plus 3 root 2 sine 3 omega t plus 30 degrees. Right. So at this point, the question is saying we should find the RMS of this. And this is a harmonic because it has a DC value. It has the first harmonic and the second harmonic. So I just take my big square root, right? I find 2 squared plus my peak value 5 on root 2, right? All squared. I find my peak value 3 root 2 over root 2 all squared, right? So at this point, this is simply going to give me 5.05 amperes, and I'm good to go. So this is how you find for harmonic waves. Now let's go to a nice concept in AC which we call phases. Phases. What is a phasor? Because sinusoidal waves are graphical in nature, we need something to represent them when you want to draw and analyze AC circuits. So a phasor is just a simply straight line with an arrow, where the length of the line gives us the magnitude of our alternating parameter or alternating quantity, and the direction gives us the phase difference. So you can have a voltage and a current moving in the same direction. What we say is that they are in the same phase. The angle between them is what, 0 degrees. So your voltage and your current will be in the same phase. A case where your voltage will move this way and your current will come down like this, I, you realize there will be an angle here between them. This is what we call the phase difference or the phase angle. And in this case, this voltage here is leading the current by this angle. So the current needs to cover up this angle before it can reach here. So this is how the voltage and the current will maintain within the connecting wire or conducting material. That is, it will continually to lead the current. So this phasor diagram or phases is just a graphical representation, a simple form to represent our alternating quantities instead of using the pulsating nature of the alternating circuit. So in this section, you'll be asked to be finding the voltage differences of phase differences, of the various quantities. So now let's see. We have an example here. Find the phase angle between the phases below. So between the phases below. So to find the phase angle, I have one phasor to be this way. This is the vertical at an angle 60. So this is V1. I have another phasor which is V2. So the problem is find the phase angle between the phases below. So I have voltage 1, voltage 2. How do I find the phase angle? So this is simply done by, it's a vector form, because this is 60 away from the vertical. So we can draw the vertical and reproduce our two waves. So we realize that this is falling here, right? And it's 60 here. This is straight, right? So that is coming from below. So it's coming from below straight away to meet this. So we always make sure that they meet, right, to get an angle between them. So this is our V1, this is our V2, right? So you realize that the angle here, what's the angle here? This whole place is equal to 180, and here is 60. So meaning here and here is 120 degrees. So our V1 is leading. So let's see. Okay, this one is rather pointing downwards and this one is moving up. So we need to turn the V1 instead. So rather it's the V2 that is leading. So see, let me draw it here. Then this way. Right. So this which is V1, and this, which is V2, you realize that we need to turn this with across an angle of what, 120, before it will be like what, this V2. Is that not it? Because we are moving. So meaning that our V2 is rather leading the V1 by 120 degrees. So the phase angle with the question asks us to find is 120 degrees. That's all. Now let's take another example. So I have example, a 50 hertz so I have a 50 hertz source which is having an RMS voltage VRMS, right, to be equal to 240 volts, delivers an RMS current, so IRMS is equal to 10 amperes to a circuit, and you see the current lags the voltage by 30. So I was using lead. Now the opposite of lead is what you call lag. If you are leading me, then I'm lagging behind you, right? So you say the problem I'm having now is saying that our current is lagging. Our current is lagging. So if you are lagging, we use negative. If you are leading, we use positive, right? So the current is lagging by 30 degrees. So meaning it's negative 30. The question is draw the phasor diagram for the circuit. Draw the phasor diagram. You know, phasor diagram deals with arrows. But before we draw the arrow, we need to know which quantity is leading, which one is what's lagging. And here you realize the voltage is leading since the current is lagging. So the voltage will move up, the current will move down, because it will have to turn 30 degrees before it will reach this side. So here's our current, here's our voltage. Now, the next part of the problem is express the voltage and current. So express I and V as a function of time. So I have the voltage and current. So we've been asked to express them as a function of time. So meaning that our voltage V, which we know in the function of time, capital Vm, which is the peak value, sine 2 pi ft. And since the voltage is leading, it will be plus the phase angle, right? Then the current I is simply equal to capital Im sine 2 pi ft minus our phase angle. So at this point, I have this as a general representation. So we've been asked to express these two quantities in this form. What's my Vm? I have my VRMS to be 240, and you know that VRMS is equal to Vm over square root of 2. So my Vm will be equal to square root of 2 times the VRMS. So at this point, I'll just multiply square root of 2 by what? My 240. Square root of 2 by 240 to get my voltage in So to get my voltage in the peak form, and what is this giving me? So I'm getting this to be equal to 240 root 2, right? You can choose to multiply and simplify to get your answer. Then sine 2 pi ft then plus the phase difference since the voltage is leading, so it will be 30 degrees, like this, as simple like that. The same for current, which is 10 amperes, so you get 10 root 2 because it's also the VRMS form. Then sine our 2 pi ft minus 30 degrees, and that is the whole concept here. So at this point, let's quickly go to addition and subtraction. So addition and subtraction of phases. So how do we add phases? Phases are not just scalar quantities. They have directions and they also have magnitude. Because of that, you need to express them into their respective component before addition or subtraction can be done. So let's see. Let's take this problem. I have v1 of t to be equal to 60 sine omega t, and v2 of t is equal to 80 sine so 80 sine omega t minus 90. So the problem is find v1 plus v2 and find v1 minus v2. So what is v1 plus v2? I can't just add 60 to 80. No, it doesn't work that way because it's a vector quantity. So at this point, this is what we do. We apply the principles of vectors here. S component, then you have the y component. So if you have the x and y components, you resolve both v1 and v2 into the x and y components. So you write your v1 here, you have its x and y components. You write your v2 here, you have its x and y components, right? So at this point, we use the phase angles to be the angle we would talk about. So let's see, watch closely as I solve this problem. So S component is always your peak cos, your phase angle. So let me write it here. So Vm cos the phase angle, then the y part, so this is the x, the y part is equal to the peak sine the phasor angle or the phase angle. So here I'm going to get 60 cos the phasor angle here is 0, phase angle, then here will be 60 sine 0. Now let me come to v2. V2 I'll have what, 80, right, cos, and I have what, negative 90. Then here I have 80 sine negative 90. So getting this, you only have to sum up your total s components, you sum up your total y components. You know 60 cos 0 is 1, so you have 60. Then you have 80 cos negative 90. Cosine is an even function and cos 90 is 0. So you simply get 0. Here, so the total x component is 60. When you come here, sine 0 is 0. So everything here becomes 0. But sine 90 is 1. So I'll have negative 80 here. And you know, negative 80 plus 0 still gives us this. So at this point, this is what I'm getting here. So I have my V1 plus V2 to be equal to 60 negative 80, right? In a vector form. What you're going to do is you find the magnitude of V1 plus V2. And this is equal to the square root of 60 squared plus negative 80 squared. And this simply gives us, so let's take, if you have 6 and 8, realize that you get what, 100. Is that not it? So you are going to get 100. Then we now find the angle, or what you call the phase difference, and it's simply equal to the tan inverse of y on x. It's the same thing we've been doing in vectors. So tan inverse of your y component over x, and here I'll have tan inverse of my y is negative 80 over x, which is 60. And this is giving me tan inverse of this, and the answer is equal to negative. So let's see something here. For the angle, before we find the angle, this is what you're going to do. Because we need the phase difference between them, we can either redraw the circuits or we can find the angle before we confirm. So what's the angle here? The angle is negative 53, right? The angle is negative 53. Negative 53 degrees. For that reason, we have 100, which is the magnitude, sine our WT minus 53 degrees. And this is simply V1 plus V2. And you realize that your V1 has X component, which is positive. So on the positive line, but the Y component was negative and will fall here. That is our V1 plus V2. So here was the 80, which is in the negative dimension. Then here is the 60. So this is our V1 plus V2 line here. V1 plus V2. We treat it as vectors. So this is all that we have here. Now we can do the same for V1 minus V2, and it's almost the same as what we've done. You simply have to subtract this and this. Your various components is still 60. When I subtract, I get my positive 80. Now since I'm getting positive, my magnitude remains the same, but this one becomes positive because I get 0 minus minus 90. 0 minus minus 90, making it positive 90, giving me positive 80 for the minus. For the minus, I'll have 100 sine of the expression omega t plus 53. So we realize that the change in sign has also changed the sign of the phase angle or phase difference. So this is simply how we add and subtract our phasor diagram or our phases. Now let's take one more example under addition and subtraction. So now we have 4 conductors meeting at a junction, and we have I4 to be equal to I1 plus I2 plus I3. This is from KCL. So it's just an application problem here. So we have this current, but this is not a DC. It's rather AC. So let's see the component of the current. My I1 is simply equal to 5 sine omega t. My I2 is simply equal to 8 sine omega t plus pi on 3. And I hope you understand pi on 3 because the angle is now in radians. Then we have I3 is equal to 15 sine omega t minus pi on 4 plus another component 8 sine 3 omega t plus pi on 3. So this is an application of harmonics. Please open your eyes carefully as you solve this problem. The problem is find I4. Find I4. We have to find I4, meaning that we have to add I1, I2, I3. So we have to find I4. So as from the example we just solved, before you can solve such problems, you need to break each component into X, Y, Z and you add them. So let me write I1. We have I2. We have I3. But you realize that the frequencies are not the same. You can never add two waveforms of two different frequencies. You don't do that. So the frequencies must be the same. Here is omega t, we can add this and this. Here is omega t, we can also add this component. But there is a 3 omega t, which you have to do that separately, right? So at this point, I'll have the S component and I'll have the Y component somewhere here. So for the S components, for the I1, it's just a straight one. I simply have to 5. I told you that is our IM, the peak, cosine, the phase difference. The phase difference is 0 here. So 5 cos 0, right? Here becomes 5 sine 0. This gives us what? 5. This gives us 0. When I come here, the phase difference is pi on 3, which is the same as 180 on 360. So I have 8 cos 60. Cos 60 is half, so you are getting what? 4, right? Then we are having 8 sine 60, which is giving us, so sine 60 is 0.860. So let's hold on with the computation. Then that is for I2, right? Then for I3, I have two different frequencies. I have omega t and I have 3 omega t. So let me write omega t separately, then 3 omega t. So this is 3 omega t. So for the cosine or the x component of the omega t, we are having 15 cos negative pi on 4, right? Then we are having here to be 8 cos pi on 3. For the 3 omega t, we are having 8 cos pi on 3. See how I have differentiated them. So within the s components of I3, we have two separate s components. 15 cos this, 8 cos this, right? So we are going to have this side to be omega t 3 omega t. So my omega t here is also 15 sine what? Negative pi on 4. Then 3 omega t is what? 8 sine pi on 3. So at this point, this gives me what? This gives me what? I told you sum all. You realize that all these are omega t. Here didn't have 3 omega t. So let me separate them once again. So at this point, I'll sum like frequency. So all this side. So I'll have here my x component. I'll have 5 plus 4. Then plus what? 15 cos negative pi on 4. And that will simply give me 19.607. Just punch it directly to your calculator. And for the y part for the omega t, I'm having 0 plus 8 cos 8 sine 60 plus 15 sine negative pi on 4, and that is giving me negative 3.678. So now this is for the omega t aspect. I have the x and I have the y, right? So as usual, you find the magnitude of this. So the magnitude is simply square root of 19.607 squared, 607 squared, right? Then plus negative 3.678 squared. That is for the omega t side. Then this is simply going to give me 19.949, right? Then I'll have my angle or the phase difference to be equal to tan inverse of the y part, which is negative 3.678 all over my 19.06, 607 instead, and that is giving me negative 10.62. So at this point, I'll have the first part, that is different harmonics. I'm going to have 19.949 sine open brackets omega t minus 10.62. But we are not done. This is for the omega t, that is one harmonic plus. Now let's come to this side. So for this side, for the omega t aspect, when I add this, it only have one x component. Then let me see. So actually, from what we are solving, I gave so for our problem, yes. So from the question I gave above, I have only 8 cos pi on 3, that is 8 cos 60, giving us 4 as a 3 omega t, and 8 sine 60. So what is 8 sine 60? So we are getting 4 for the magnitude, 4 squared plus 8 sine 60 all squared, right? So I'm getting something like 6.9 for this. So 4 squared plus 6.9 . So 6.928 squared. So what am I getting for this side? So I'll simply take the square root of 4 squared plus 6.928 squared. And that is simply equal to 7.99999, which is approximately 8. So I'll have plus 8. So this is my final answer. I have plus 8 sine. Here is 3 omega t. Take notes. Yes. But the phase difference will be tan inverse of what? So I'll have tan inverse of the expression, my denominator, which is my y part, which is 6.928, over the x part, which is 4. And that is giving me 60 degrees, almost 60 degrees, right? So I'll have plus 60 degrees, and this gives me the value for I4. So in these problems, just add the corresponding frequencies. You can only add two frequencies which are like. That is why our waveforms had different frequencies, but we couldn't add all together. So you add omega t. So if you had gotten different harmonics, you do separately to get this. So thank you for being with me for this section of our AC class. We will continue from impedance, then we move through to using complex numbers to represent impedances and others. Thank you once again.